All right, welcome everyone to Debugging 101. My name is John Bunting. I'm a graduate teaching assistant at Virginia Tech's Bradley Department of Electrical Computer Engineering. And today we're going to be discussing debugging tips and tricks and how to debug your C code and write more efficient code that is less prone to error. So the first thing we need to discuss is, why do we care about debugging? Well, how many of you, while trying to write some C code for this microcontrollers class, have ever looked like this? Or maybe this? Many of the projects that we have you work on, including the upcoming Lab 4, are incredibly difficult problems to work on. They're large in scope and they require a lot of creative thought and discipline in order to break these problems down into simple parts and to solve them in code. So the goal of this session is to translate that frustration that you have while working on some of these difficult problems into fight. We want to empower you so that you don't become frustrated anymore, and instead you have a series of steps that you can follow in order to solve your problems instead of staring blankly at your screens and feeling helpless. So how do we do this? Well, there are three main steps to debugging. The first is identify that there's a problem. The second is isolating that problem. And step three is give up. Seriously. Step three is give up, and we'll explain a little bit more later on in the video why this is a key step to the debugging process. But let's go ahead and break this down into step one. Identifying there's a problem. This is the part that we are typically very good at. When our code doesn't build, it's very easy for us to see that something's wrong. Or if while playing a game on our microcontroller, we see that it is not performing the way we expect it to, or is doing behavior that we think is inappropriate or not what we intended to, then we know that there's something wrong. The real trick comes in step two, when we are isolating the problem. This is where debugging techniques actually come in. Debugging is intended for us to identify where our problem is, to slow down our code, and so that we can isolate where this problem is and fix it quickly and efficiently. Before we can actually debug our problem, we need to ask ourselves one question. Does our code build? Because when our code does not build, then it is impossible for us to use the built-in debugger in Code Composer Studio. I wish I had a better answer for you all, but when our code does not build, genuinely, the best avenue of approach to solving these problems is Google. Whenever you encounter a problem or an error message in Code Composer Studio that doesn't make sense to you, maybe this doesn't look like English, I've never seen this type of an error before, that's okay. Go ahead and type that error into Google and see what results pop up. If you have ever done this before, I'm sure you're very familiar with a lot of helpful feedback that is found on websites like Stack Overflow. Additionally, Code Composer Studio and the microcontrollers that we are using for this class are manufactured and developed by Texas Instruments, which is a very reputable company. And because they are a reputable company, they have an entire community of engineers that make up this E2E forum, or this E2E community, and it is their job to respond to issues that software developers have with their equipment. And because we all purchase these boards for you, you all, in this class, are professional software developers. And so you are able to ask them questions on their community or on their forum post, and they will respond to you to help you, give you some answers. More likely than not, though, you will encounter problems that people have run to in the past. So Stack Overflow, or just searching through the E2 community of other posts that people have had, should help you solve most of your problems. When our code doesn't build, that can be frustrating. But I think all of us might agree that when our code does build and it still does not perform the way we expect it to, that can be even more frustrating. We've spent hours on our code, we've labored over it, and it finally builds and we expect it to do what it does or what we expected it to do, and it doesn't perform the way we want it to. Now this is where we get the debugger involved. Our microcontrollers and computers in general are incredibly wonderful for us to use because they can perform operations at a much higher speed than even humans can. But when our microcontrollers or computers are malfunctioning or behaving abnormally, it can be hard for us to find out where the issues are when a computer or a microcontroller is moving so quickly. The debugger allows us to slow our code down so that we can visually see exactly what's going on at our speed. Whether you know it or not, every single time you've run your code thus far in your class, you have been using the debugger. The 3 buttons on the left are the ones that I guess you are most likely familiar with. The Start Resume button that looks a little bit like a play button, the Pause button, and the Stop Exit button. Whenever we run our debugger in Code Composer Studio, the code is compiled and ported to our board, and before it runs, the debugger halts the program right at the beginning of main. And when you hit this Start Resume button, the debugger starts running and will continue to run until it encounters something called a breakpoint. We'll discuss that a little bit later. The 3 buttons that I want to make you aware of that are incredibly useful to using the debugger are the 3 on the right that you might not be familiar with. These 3 buttons are Step Into, Step Over, and Step Return. And the best way to see how these actually work is to use an example. Here is some code that was written for a microcontrollers class. Homework 5, Part 3. What I'm going to do is I'm going to run the debugger on this code. And as we said earlier, it is going to port to my board and compile. And now the goal of this exercise is for us to slow down our code and to identify where we think there might be a problem. So this code is something new to me. Let's say that I've never seen this code before. These were some functions that were given to me by my professor, and I'm not entirely sure what they do. And so I'd like to step through these functions line by line and visually see what is going on my board. The debugger is very convenient and allows us to do this through something called a breakpoint. Now to set a breakpoint, let's go to line 53, for example. Let's say this init graphics function is something that I've never encountered before, and I am suspicious, and I think this might be causing some issues in the run performance of my code. I'm going to double click on 53, the line number 53, and you will see this little green diamond appear to the left of the line number. This is a breakpoint. What will happen when I resume my code is it will continue to run my code in its entirety until it encounters one of these breakpoints. And when it does, it will halt at this line and not execute the line of code that the breakpoint was set at. Let's see this. As you saw, when I hit resume, the highlighted green box over the int main void, the beginning of our main function, was replaced at the init graphics. What this means is that my code has executed every single line from line 45 to line 53, but not including line 53. Now, using the 3 step functions that I mentioned earlier, let's investigate the init graphics function. Instead of just executing the entire function, I want to see the individual parts that are at play inside of this function. When I want to do this, I'm going to use the first of our 3 buttons, the Step Into button. When I click this, my code jumps to the function that I'm trying to call, but does not execute it. This enables me to step through my code line by line and see exactly what is going on inside of my code. Now, let's say that inside of this function are some additional functions. But let's say that I've used these before. For example, these graphics init context functions. These are a part of my graphics library, and I trust that the software developers at Texas Instruments know what they're doing when they develop them. So there's no need for me to investigate further or deeper into these functions. I just want to execute them and remain at the same scope inside of my init graphics function. To do this, I will use the second button, Step Over. What this does is executes the current line of code in its entirety, including any lines of code that it's dependent upon. To see this in action, let's click on it a couple times. Here, Crystal Font Z 128 by 128 init is a function that I am calling, but I do not want to investigate any deeper into it. So I will click Step Over, and the entirety of that line of code was executed, and we have moved on to the next line of code. I can repeat this as often as I want and to execute as many lines of code as I want, stepping through my code line by line as slowly or as quickly as I need to in order to understand exactly what's going on with my code. Now lastly, let's assume that all the remaining functions in this function that I am investigating are functions that I trust. I know that these are going to perform the way they should. But instead of just resuming my code, I want to jump back out to my main so that I can continue to investigate additional lines of code at the main level. That is where our third button comes in, Step Return. When I click Step Return, the remaining 4 lines of code in this function, lines 22, 23, 24, and 25, will all be executed. I will complete a init graphics function, and I will jump back out to my main. And now we are back out in our main at line 54, and we have completed stepping through init graphics in its entirety. We can continue to use the Step Over button to continue to run these functions at a high level. Now that we've reviewed a little bit on how to use breakpoints and how to use the step functions, let's talk about some other types of problems that we can solve using our debugger. Breakpoints and the step functions are incredibly useful for monitoring the flow of our code. If we are trying to, for example, make sure that a state machine is working correctly, we can set breakpoints at the beginning of a state that we expect to enter on a given event. For example, when we press a button. I can set a breakpoint at the beginning of a state that I should only ever enter when a button is pressed. And if I hit the Start Resume button, my code should operate as normal until I press this button. That will trigger the event that enters my state, and my code will run into my breakpoint, and only then should my code stop. From here, I can continue to jump from state to state and slow my code down to visually verify in my Code Composer Studio that it is going where I expect it to and only when I expect it to. So breakpoints and step functions are incredibly useful for monitoring the flow of our code. But what happens if we suspect that the issue is with the values of our variables? The debugger also has a solution for this. The debugger has an operation built into it called watching variables. And even we can build upon watching variables and actually create our own expressions that we can use to make sure that our variables never leave outside of our expected scope. Let's use an example of this too. Going back to Code Composer Studio, I am still in my debugger and I am still paused at line 56 at Start ADC. Here you saw when I ran the debugger, this variables window popped up automatically, and it has identified 3 variables that I might be interested in looking at. Our unsigned integers vx, vy, and random bit. Not always will this variables window pop up upon running our debugger. In order to get this window to reappear after I've exited out of it, simply go to View and Variables. Now as you can see, currently all of my variables have some incredibly random values. The reason for this is we haven't even gotten to the line of code that initializes our variables yet. Let's go ahead and set a breakpoint down here at line 64. After we've initialized vx, vy, and random bit, and we've called this line of code getSampleJoystick that samples our joystick and puts the respective values inside of our unsigned integers vx and vy. When I hit resume, my code will execute through all of the lines of code between line 56 and stopping just before line 64. As you can see up here in our variables window, our values have been updated. Because they have been updated since the last time that we executed our code, they are highlighted in yellow. Since running line 58, we can see that our random bit has now moved from a jumbled mess number to our expected value of 70. And our unsigned integers Vx and Vy have been given their values from the analog to digital converter on our board through the joystick. An example of how to verify values and using breakpoints in the debugger. Let's say, for example, that I am new to using the joystick and I want to know what values my ADC is producing when I read values off of the potentiometers that make up the joystick. What I'm going to do that you will not be able to see is before I resume my code again, I am going to move my joystick to the right. Now that I have fixed my joystick in the right position, I am holding the joystick in the right position, I am going to resume my code so that it executes through one entire loop of the while loop, rereads the joystick, and gets back to random bit at line 64. After executing this, we can see that my Vx value has changed from around 7,000 or 8,000 to 14,500. This is an incredibly easy way for me to verify values of my variables instead of using printf statements to print to the console or to printing to a screen or some other debugging method. Now I'm going to repeat the exact same process, but hold the joystick in the left down position. When I rerun my code, let's see what the values of Vx and Vy become. Now, instead of around 8,000 or even 14,500, my values have been updated to around 1,500 in the Vx direction and 4,100 in the Vy direction. When dealing with new hardware, this is an incredibly useful feature, or just monitoring state variables or any other variable in general. Additionally, we can use an expression to verify that our variables never go outside of a expected behavior or expected threshold value. In the same way that we got the variables window to pop up, we are going to go to View and Expressions. This window will pop up just below the variables window, and as you can see, I've already predefined a couple of expressions here. Instead of just checking the values of my variables, let's say that my Vx value should never go above a threshold of 10,000. And as long as it doesn't go above a threshold of 10,000, I will be happy. I have created this expression, Vx is less than 10,000. And here we can see the value that this expression is producing. Because my current Vx value of 1,591 is less than my threshold value of 10,000, the value that I am producing is a 1, or in this case, true for the current Boolean expression. I can do more advanced expressions as well. For example, creating a more advanced Boolean expression in which I set both a lower bound and upper bound on my Vx value. Or I can even use more advanced mathematical operations. To add a new expression, simply click Add New Expression and type in your expression here. When rerunning my code, now that I am no longer holding the threshold or holding the joystick in a particular position, the expressions will update alongside my variable values. Here, you can see that now that my joystick is returned to the neutral position in its center, the Vx value is still less than my threshold value of 10,000, so we are producing a 1, or a Boolean true. My second expression, however, has been updated to a 0. This notifies me that, hey, my Vx value is outside of this expected threshold, that it should not be. Maybe something is going wrong. I hope you found these debugging tips and tricks incredibly useful. And as promised, we are going to cover step 3 of the debugging process. Give up. Why do we say give up? This is not intended for you to stop becoming or quitting your aspirations towards becoming a software developer or even completing your degree. Give up simply means that we should not be caught up in our own ways of thinking for too long. Oftentimes, when I am trying to help students, I see students that are attempting to solve the exact same problem for an extended period of time, which is incredibly frustrating. As an engineer, we are problem solvers, and problem solving is inherently a creative process. Don't let anyone tell you otherwise. Occasionally, when we are trying to solve problems, our initial approach will not be the best approach, and that is okay. Don't get frustrated. The metric that I encourage students to follow is that if when trying to solve a problem or debug a problem, and you have been trying to debug this problem for longer than 2 hours and have not been making any progress whatsoever, it might be time to give up. Take a break, relax, go watch TV or take a walk around the block, and return to your computer fresh and ready to approach the problem from another perspective. Occasionally, or oftentimes, it will be easier for you to approach the problem from a completely new perspective than to fix the problem that you've already been trying to solve for an extended period of time. Now that we've covered the 3 steps of debugging, I want to leave you all with a couple of tips and tricks on how to write good code that is easy to debug. My first tip: do not use printf if you have a debugger. The purpose of our debugger, as you remember, is to slow down our code. Printf statements, while also monitoring the flow of our code, do not slow down our code, and they can become incredibly difficult to follow if they clog up our console. Additionally, many of the problems that we are going to try to solve are incredibly overwhelming. Lab 4, for example, or if you want to be a software developer, any problem that you will be trying to solve in your professional career. I encourage you, or I remind you, please don't get overwhelmed. The 3 best things you can do to not get overwhelmed when trying to break down a difficult problem are designing your code before you start typing. I know it can be tempting to just jump right into the problem and start typing code, but the best software developers design their code in its entirety from the top down before they even start typing a single line. Make a blueprint for yourself. Know exactly which functions you're going to write, what parameters they require, what values they will return, and how they will work together to solve your overarching problem. After you've created a blueprint for yourself, all you have to do is follow your own steps. My second recommendation is to incrementally develop and test. Too many times I see students writing hundreds of lines of code at a time before building or running their code. If you encounter a problem, which more than likely you will, because as developers we are error prone, it will be incredibly difficult to isolate this problem because now there are hundreds of different places where your problem could exist. Instead, incrementally develop and test. Write one function or even parts of a function at a time. Verify and test their behavior before implementing that code in a larger system. That way, when you do encounter problems, it will be easier to identify what is and is not working. And lastly, use virtual functions. Now, many of you probably are not familiar with what a virtual function is. There are many names for virtual functions, but essentially, what a virtual function allows us to do is to verify the behavior of code that is dependent on other code. For example, if we are using a joystick for the first time, and we want this joystick to, for say, move an obstacle along our screen, or translate an obstacle across our LCD screen, both of these functions are incredibly difficult and could have a lot of potential for error. Instead of using the joystick or developing the joystick and developing the screen functions and testing their behavior with each other, let's isolate each part of this system. How about instead we verify the joystick behavior, and instead of translating a car across the screen, we use a function that we know will perform correctly so that we can verify our joystick is performing the way we want it to. My favorite example is to use a toggle LED function. When using your joystick, move the joystick in a certain direction and verify its behavior by toggling an LED. Once you have seen that your joystick is performing the way you expect it to, then move on to the second piece of code. If you want to use a virtual function to test your car first, what you can do is use an event-based system that you know performs correctly. For example, if you've already debugged a button, instead of using the joystick to translate the car across the screen, use a debounced button to translate the car. That way you can verify each of those functions' behavior and then combine them, and there should be very little problems or very few problems when implementing them together. That's all I have for you. Thank you so much for sitting in on this Debugging 101 session. I hope you learned a lot about how to use a debugger and how to debug your code and how to write code that is easy to debug.